There are two fundamental types of patterns: design patterns and business logic or domain patterns. Design patterns transcend any particular application. For example, the factory pattern, which we used in a previous unit, could be used, where appropriate, in any kind of application. On the other hand, business logic patterns reflect the type of application being built. For example, in a particular industry, if customers and orders are related in a certain way, because that's the way the relationships work in that industry, that is a domain pattern. Domain patterns emerge out of domain-driven design. Since our sample app is generic and very simple, we can't really discuss business logic patterns. Nonetheless, it is important to understand the distinction and for you to think about patterns for your particular area of industry expertise. Nonetheless, design patterns and interface-based design can be used within the domain model to partition and layer the domain model. We can, however, describe patterns to organize the business logic. Fowler describes three architectural patterns to organize the domain logic: transaction script, domain model, and table module. Transaction script is probably familiar to everyone. The application takes the user input, processes the input, and stores the result, and often displays some sort of result to the user. There is a one-to-one correspondence between user actions and application functionality. Typically, you have create, read, update, and delete type of operations. And the database code is straightforward. And results can or cannot be displayed to the user. The problem with transaction script is that as the business logic becomes more complex, the processing becomes too complicated. If the various user actions share multiple complicated processing paths with multiple options in each path, the code logic in transaction script can be very convoluted, and there's minimal code sharing. Suppose, for example, adding a customer required finding out what kind of customer it was, and that depended on their credit rating, the types of products they were interested in buying, their geographic area, characteristics such as the size, and what kind of customers they had. Other actions might want to share the same functional units. So using a rich set of objects becomes much more attractive than procedural logic. Both the domain model pattern and the table model pattern use objects, but they use those objects in a very different way. If there's a direct correspondence between the tables in the relational database and the user actions, a table module pattern can be a very attractive approach. Every class corresponds to a virtual database table. By virtual database table, I mean some set of data. It might be created by a join that corresponds to some conceptual unit that the user views as a table. And you can use a record or a data set to interact with the database. You're still basically dealing with CRUD applications, and it's good for applications with a minimal business logic complexity, but perhaps having complicated data relationships. Not all applications have this simple relationship with database tables. And when you use a table module, evolving the application can be more complex, because you lose the full power of object-oriented programming techniques, because basically you're using a record set or a data set to interact with the database. This gives you a closer coupling between the business logic and the data layer. For example, as you get multiple order types, the table module pattern will have one class to handle all the orders, and each order would be identified by an ID. The domain model pattern uses classes to model the entire set of business logic. We then can use the technique of interface-based polymorphism that we discussed in the first unit to partition, layer, and evolve the application. In the previous order type example, each order type would be modeled with a separate class. Each order would be a separate object. Hence, it would be easier to separate out different ways of handling different orders and share functionality into shared classes that these different order types use. And these functionalities, of course, would be represented as interfaces. The domain model, however, does not come without a cost. Complicated object models often do not map well to relational database models. In a relational database, all the data is available to do joins and unrestricted operations. There is no encapsulation. data is tightly coupled together by the schema, and you have a limited number of operations. Objects have a high degree of encapsulation, and with no schema, each object can define its data and behavior independently. This can complicate query logic and make writing ad hoc queries difficult. Object relational mapping, as we'll discuss in this unit, can make this job easier, but does not remove the problem entirely. The decision of which to use obviously depends on your application's characteristics and complexity. We will work through the remainder of these units as if we had a domain model. Why did I make that choice? First, unless you know that your application is going to stay simple, the domain model approach will allow your application to evolve. Simple domain models will have few, if any at all, real object relational mismatches. Changing from a transaction script or table module pattern to a domain model pattern is difficult. The code conversion can be complex, and programmers who start down the transaction script or domain model path often do not understand how to use a domain model pattern. Complex domain models generally have benefits that outweigh the object relational mismatch unless end users write a lot of ad hoc queries. Given those benefits, for pedagogical purposes, and for these reasons which I outlined before, we will assume a domain model pattern. Of course, how to write a domain model is beyond the scope of this set of units. Books by Eric Evans and Jimmy Nielsen are two good references on the topic. So then the question becomes, how do we isolate the database logic? This is one of the most important isolation layers in any application. To achieve that isolation between your business logic, whether it's a domain model or a transaction script or whatever approach you use, and the database code itself. Usually this data store is a relational database. And when you achieve this isolation, you can modify the business logic without impacting the database storage and retrieval code. And you can modify the database storage and retrieval code without changing the business logic. The set of patterns that accomplish this task are called persistence patterns. We shall focus on two of these persistence patterns, data mapper and repository. And even if you use storage mechanisms other than a database or a business logic pattern other than a domain model, this is one of the most important issues that you can confront, how to do this separation. The data mapper pattern keeps the logic and database layers independent while moving data between the database and the objects. Our choice of this pattern was largely dictated by our decision to use a domain model. Object relational mapping products implement the data mapper pattern. Many of them allow for object queries that can be used in a similar fashion to SQL queries. They also provide data transactions at the object level. With these and other features, they help alleviate the object relational mismatch. To give you an idea of how the data mapper pattern works, we have implemented a very simple object relational mapping layer in our application. To keep things simple, we are not going to implement features such as lazy loading, identity maps to see if objects are already loaded, or reflection to provide complete independence between the domain model and the data mapper. An ORM can also pull in an object tree. In a real application, you would use a commercial production that provides these features rather than create your own, unless you had a very simple data mapping layer as we have in our application. Our data mapper is based on a simple interface, iCustomerDataMapper, which provides just three primitive operations: delete, save, list. Save handles both creating a new instance and updating an existing instance. Interfaces are used as parameters to the data primitives. They are not bound to any particular implementation of a customer or how the data stored with the customer is generated. The domain layer also has no knowledge of how the data is stored. Right now, data is stored in a sorted list instances. In a later unit, we'll use a relational database with no need to change the domain model. Notice that the Customer Manager constructor takes an iCustomerDataMapper interface. This technique, which we'll discuss in the next unit, is called dependency injection. Instead of having the Customer Manager create an instance of an object that implements the iCustomerDataMapper interface, the instance is associated with the Customer Manager at the constructor. The code in the customer manager uses this interface, and thus the customer manager implementation is not bound to any particular data mapper implementation. Applications need a mechanism to find existing objects. Our data mapper layer maps objects to relational tables. Hence, we need a query mechanism that queries objects, not relational tables. This is what the repository pattern does. If you have a very simple application, simple data access methods to do simple queries might be enough. But if you have a more complicated application, a repository pattern fits the bill. Our example is a very trivial example of how a repository pattern would work. Most ORM products implement some form of repository. Our criteria class represents the simple criterion used in our repository queries. We specify an operator and an operand for the query. The operators can be all, ID, or name, depending on whether we want all instances, a query based on an ID or name. The operand represents the value used in the query. For example, if I want the customer whose ID is 4, the operator would be ID and the operand would be 4. The query method returns a collection of objects. The repository uses the data mapper in its implementation. Again, an interface is passed into the custom repository constructor using dependency injection, so we are not assuming any particular data mapper implementation in our implementation of the repository. Using the repository pattern allows developers to construct queries in terms of the objects they are using without having to understand the details of how the database is implemented or the intricacies of whatever SQL dialect the database uses. Even in our simplistic implementation, asking for a customer brings back the related order. The repository pattern allows the developer to think in terms of the domain objects in which they are programming. They get back a fully instantiated chain of the objects they need without having to worry about how to reconstitute them from the data store implementation. So to summarize, while domain patterns are industry specific, the idea of separating the business logic from the way data is stored in the database is fundamental. We have used interface-based design to look at two key persistence patterns, data mapper and repository. While these are not the only persistence patterns, they illustrate two critical elements in a data hiding layer. Hide the details of the database implementation and provide data access in terms of the programming concepts and abstractions used in the business logic layer.